In this video, we'll be learning the method of splitting the numerator, which will help us to compute certain integrals. So the first example is integrating x squared minus 1 divided by x squared plus 1. Now in this example, we have a rational function where the numerator and the denominator have the same degree. Okay, they're polynomials both of degree 2. Now whenever we have a rational function where the numerator has a degree equal to or greater than that of the denominator, we usually want to do a polynomial long division in order to reduce the degree of the numerator. Okay, and this would be a case where we would do such a thing. We would do a polynomial long division here. But as you might know from experience, polynomial long division is a bit time consuming. So we might try to look at another way of doing this. Now the way that we're going to do it is we're going to realize that the numerator and the denominator are pretty much identical. They're only differing by this minus 1 and plus 1. And it's very easy to manipulate this into something that's much easier to work with. So if we write what we have in the denominator in the numerator, so if I write x squared plus 1 in the numerator, what I've actually done is I've added 2 to the numerator. So what I need to do is I need to subtract 2. So now I still have x squared minus 1 in the numerator, but it's just written in a different way. But what I can do is I can put brackets around this, and then I can see that I'm able to split my numerator now. I can split it into 2 separate fractions. So I'm left with x squared plus 1 divided by x squared plus 1 minus 2 divided by x squared plus 1. So now I have 2 fractions. Of course, the first fraction is just 1. It's something divided by itself. So that's the integral of 1 minus 2 over x squared plus 1. And we should know from both the previous video and from the 3-unit course, we should know how to integrate that second fraction there. That's just an inverse tan. So this is going to be the integral of 1, which is x, minus 2 times tan inverse plus c. So what you can see is that instead of doing the long polynomial division, or the polynomial long division, we've actually just rewritten the numerator in a specific way. We've been very clever in how we've done it, and then just split the fraction into 2 by splitting the numerator. Okay, and it's helped us to solve this integral. Okay, and that's the first example. The second example is the integral of 3x plus 5 divided by x squared plus 2x plus 4. So in this example, as in the first one, we have a rational function. So that means it's something of the form p of x divided by q of x. But in this case, the degree of the numerator is less than the degree of the denominator. So we also have that the degree of p of x is less than the degree of q of x, which means that we don't need to do any polynomial long division or any of the manipulations as we did in the first example in this example. Okay, so we have the degree of p of x less than the degree of q of x. And we have a polynomial of degree 2 on the bottom and a polynomial of degree 1 in the top. That means that there's going to be a logarithm in our solution. Now, in the final answer, it might not just be a logarithm, there might be other things involved, but we're definitely going to get a logarithm. So we want to try to write p of x in the following way. We want to write it as a constant times q dash of x plus something else, and that something else has to be another constant. The reason it has to be another constant is because we want all the x terms in the numerator to be included in this first term, a times q dash of x. And you can see that when we divide by q of x, the logarithm is going to come from a times q dash of x divided by q of x. Okay, because that's the form of a log. When we integrate a function, a rational function where the denominator is a function and the numerator is the derivative of the denominator, that's going to give the log. Okay, so we want to try to work this out. Now, firstly, what is q dash of x? Q dash of x is the derivative of x squared plus 2x plus 4, which is just simply 2x plus 2. So that means we want to write 3x plus 5 as being equal to a times 2 times x plus 2 plus b. Okay, so here we can just simply equate coefficients. So the coefficient of x gives us 3 on the left-hand side and 2a on the right-hand side, which means a is going to be 3 divided by 2. And the constant term is 5 on the left-hand side, and we have 2a plus b, which means that b is going to be equal to 5 minus 3, which is going to be 2. Okay, so let's go ahead and apply this now into the integral. So we want to rewrite the numerator in the following way. A times q dash of x, which is 2x plus 2. And a was 3 on 2. So we have 3 on 2 times q dash of x, which is 2x plus 2, plus b, which is 2, divided by x squared plus 2x plus 4. Now the next step is where we actually split the numerator. We're going to make two fractions out of this one fraction here. So we have 3 on 2 times 2x plus 2 all over x squared plus 2x plus 4 dx, plus we're also splitting the fraction and at the same time splitting the integral into two integrals. So plus 2 over x squared plus 2x plus 4 dx. Now the first one, we know what that's going to be. That's just going to be a log. We can take the 3 on 2 out and then it's just the log of the denominator. So that's 3 on 2 times the log of x squared plus 2x plus 4. But for the second integral, we have a quadratic in the denominator and a constant term in the numerator. Now the quadratic is also irreducible, and we saw in the previous video that those led to inverse tans. So what we need to do is we need to complete the square in the denominator. So that's 2 divided by, when you complete the square here, it's going to be x plus 1 all squared plus 3 dx. Okay, so we can just rewrite this first bit again. Log of 2x squared plus 2x plus 4. Now for this bit, we could use a substitution, u equals x plus 1, but I think that it should be pretty easy to see that this is the inverse tan. So when we take out the 2, it's going to be 1 divided by a. In our case, a is the square root of 3. If you're not sure about this, make sure you go back and watch the previous video where we covered this style of an integral, times tan inverse of x plus 1 divided by root 3. And since there's no more integrals to compute, we now add our constant. And that's the end of the second example. The third example is the integral of the square root of 1 plus x divided by 3 plus x. So here, our function is of the following form. It's of the form ax plus b divided by cx plus d, all under a square root. So we have a degree 1 polynomial divided by a degree 1 polynomial, all square rooted. Now the way we deal with these is a little bit counterintuitive. Usually when we deal with surds, we like to rationalize the denominator. But in this case, we want to rationalize the numerator. And let's have a little think about that. What happens when we rationalize the numerator? We'll get ax plus b on top, and in the bottom we'll get the square root of cx plus d times ax plus b. Now what do we have under the square root? We have a degree 1 polynomial times a degree 1 polynomial, so we get a degree 2 polynomial. Namely, we get a quadratic function underneath the square root. And we know that if we have a square root with a quadratic underneath it in the denominator, that's not a problem. We kind of know how to deal with those. We've seen them in the previous video. So what we want to do is we want to rationalize the numerator. So we're going to get 1 plus x divided by the square root of 3 plus x times 1 plus x. If we expand out that bit underneath the square root, we'll get 3 plus 4x plus x squared. Okay, now at this point we have a rational numerator, and this is where we're able to split the numerator. But before we go ahead and split the numerator, we're going to look at a form of integral which involves the square root in the denominator. Okay, so this is a sort of a general thing, but it has to fit a certain form. So if we have an integral of the following form, the integral of, we have a fraction, and we said we have a square root in the denominator. So if we have the square root of any function, it doesn't have to be a polynomial. In this case, it's a polynomial of degree 2, but it can be any function. If we have that, and the numerator is the derivative of that function, so f dash of x divided by the square root of f of x. If we have this, then this is equal to 2 times the square root of f of x, of course plus c as well. Now, this is pretty easy to prove. We can make a u substitution, or we could differentiate both sides and integrate and do all that. We're going to look at this in a bit more detail in a later video. However, for this video, I think it's just enough for us to accept it as it is. Okay, but we definitely will go through this in another video. So, in our case, we have f of x is 3 plus 4x plus x squared. So that means our derivative, f dash of x, is going to be 4 plus 2x. Now, I want to somehow involve f dash of x in my numerator. So I need to write 1 plus x in a certain way, which involves 4 plus 2x. So this is what we need. We need 1 plus x to be equal to some constant times the derivative, 4 plus 2x, plus a remainder, which has to be a constant. I hope you can see why it has to be a constant and can't involve any other x or even higher powers of x, although obviously there's not going to be higher powers of x here, but it has to just be a constant. So what we need to do is we need to equate coefficients, and if we do that, we'll get a equals a half and b will equal minus 1. Okay, I'll leave that for you to check. That's not too difficult. Alright, but now we can rewrite our numerator in the following way. We can write it as the integral of a, which is a half, times 4 plus 2x, plus b, which is minus 1, so minus 1 here, divided by the square root of 3 plus 4x plus x squared. And at this point, we can now split the numerator into 2. Let's move this up a little. So we have, and I'm going to take out a half here, so I have a half outside the integral of 4 plus 2x divided by the square root of 3 plus 4x plus x squared. And now this is exactly in the form right here. It's right in that form, so we know exactly what that's going to equal. Minus the integral of 1 divided by the square root of 3 plus 4x plus x squared dx. Okay, so this is going to be 2 times the square root of 3 plus 4x plus x squared. That's just using the form that we wrote on the side there. By the way, this form, I'll just mention it now, this form is really a u substitution. And I already mentioned that you can prove it using a u substitution, but this is really just a u substitution without making a u substitution. Okay, so it's just a sort of a shortcut which sometimes pops up in this form, and if you can recognize it, it's fine to go ahead and use that form. And okay, we have this other integral. Now, when we were dealing with these integrals, we knew that there was either going to be an inverse sign or one of the two logarithms. And the way we determined that was by completing the square here. So if we complete the square, we'll get x plus 2 all squared, and then minus 1. Okay, so this tells us it's going to be a log. So let's actually evaluate that. This here becomes just 3 plus 4x plus x squared. And the second integral becomes the log. The log of x plus 2 plus the square root of x plus 2 squared minus 1 plus a constant. And this is correct, but this little bit in here, we can actually just do the reverse of completing the square to get it a little bit nicer. And we can write it as 3 plus 4x plus x squared minus log of x plus 2 plus the square root of 3 plus 4x plus x squared, and then plus a constant. And that's the end of the third example. The fourth and final example is the integral of 7 cos x plus 3 sin x divided by 2 cos x plus 5 sin x. So, in this integral, we have a function of the form p of x divided by q of x, where p of x is equal to a times cos of x plus b times sin of x divided by c times cos of x plus d times sin of x. So what we have is a linear combination of cos and sine divided by another linear combination of cos and sine. And what's the trick with these types of questions? Well, the trick here is to write our function p of x, which is the numerator, as the following. It's going to be some constant, I'll just call it alpha. So alpha times q of x plus another constant beta times q dash of x. So what do I have? I have the numerator is written as a combination of the denominator plus the derivative of the denominator. And why would I do that? Well, what happens when we divide by q of x? So if I divide this by q of x, I'll get the following. I'll get alpha, q of x divided by q of x is 1, plus beta times q dash of x divided by q of x. Now, can I integrate alpha? Yes, alpha is just a constant, so we know how to integrate constants. And what about beta times q dash over q? We can definitely integrate that. That's just a log. So if I can rewrite my numerator in this form, then I'm able to solve these types of questions. So for us, we have q of x is equal to 2 times cos of x plus 5 sin of x. So therefore our derivative q dash of x is going to be negative 2 sin of x plus 5 cos of x. So now we need to rewrite p of x as that combination of q dash and q. So let's use black now. So we want to write p of x. What's p of x? P of x is 7 cos x plus 3 sin x. We want that to be equal to some constant alpha times q of x, which is 2 cos x plus 5 sin x, plus another constant beta times q dash, which is minus 2 sin of x plus 5 cos of x. So what do we need to do? We need to equate coefficients. We need to get coefficients of cos of x, which is 7 equals 2 times alpha plus 5 times beta. And we have for sine, the coefficients are 3 equals 5 alpha minus 2 beta. You can go ahead and solve that, and you'll get the following. You'll get alpha equals 1 and beta equals 1. Okay, so now that we've done that, we can rewrite our integral in a certain way. We can rewrite the numerator as alpha times q, so that's going to be 1 times 2 cos x plus 5 sin x. So we'll have 2 cos x plus 5 sin x, plus beta times q dash of x, so plus 1 times negative 2 sine plus 5 cos. So negative 2 sine plus 5 cos. And then all of that is divided by the denominator, which is 2 cos of x plus 5 sin of x. And at this point, we split our numerator. So I'm going to have the integral of 2 cos x plus 5 sin x divided by 2 cos x plus 5 sin x. Well, that's something divided by itself, so that's just 1. And then I have plus minus 2 sin x plus 5 cos of x divided by 2 cos of x plus 5 sin of x. But remember, what's this? This is just some function in the denominator, and on top we have its derivative. It's q dash divided by q. So when we integrate that, it's just going to be the log of the denominator. So here we have the integral of 1 is x, and the integral of that fraction will be the log of the denominator. So 2 cos of x plus 5 sine of x. And of course, now that we have no more integrals, we have our plus c. And that's the end of the question and the end of the video.